Alright, so here we go with the part of the test where you can not use our calculators. Okay, so these are non-calculator problems. We started these in class, but I'll run through them here again really quick if we can. So first we just have to factor this, so we can see it's got to be an x times x, and we could go with 6 here. Remember, it has to multiply to 6. Well, 1 and 6 multiply to 6, and you have a difference of 5. 2 and 3 also multiply to 6. So I'm going to use the 2 and 3, it turns out, because they both have to be negative. And you can see now the negative 2 times negative 3 is positive 6. And this negative 2 and negative 3 add up to that negative 5. So there it's factored. Problem number 2 here, again a factoring problem. All we have to do is remember our steps. First, remember, is always look for that GCF. And so I can see I can take a 5 out of each of these, and also if I look at their exponents, I can take an x cubed out. So let's take that out. Leaves us an x squared minus 25. And now you do always have to check what you have left over here. This is a difference of 2 squares. And so if you remember the formula for the difference of 2 squares, a squared minus b squared equals a minus b times a plus b. And so our final factorization, x minus 5 times x plus 5. It would be this whole answer right here. Problem number 3 is x minus 3 a factor. Well, to determine if something's a factor, we can just use division. So we want to divide x minus 3 into 2x cubed minus 54. If our remainder is 0, we have a factor. So in synthetic, remember, we use what would be the 0 for this, so we'll put a 3 in there. We'll write down our coefficients. Now be careful here, we have a 2x cubed, but there are 0x squareds. There's 0x to the first minus 54. And if you remember the process, I'm trying to squeeze it in here. We bring the 2 all the way down, you multiply. 0 plus 6 is 6. We multiply. Add them up, and 3 times 18 is 54. And so it adds up to 0. So we know it divides into it evenly. So yes, it's a factor. How do you know? Divides into it evenly. Question 4, find all the roots of this trinomial here. Notice it is quadratic, and so to solve quadratics, we make sure they're equal to 0, and then we try to factor them. It's quadratic. You could always use the quadratic formula, but that'd be a little overkill, I think, for this problem. Factors very nicely. Don't forget to set each factor equal to 0 to solve them. Okay, we get lazy sometimes, and we forget to do that. Question number 5. Is 4 a 0 of this polynomial right here? All we have to do is, we could use synthetic again. You'd put the 4 in the box here, because that's what you'd be testing. And put down your coefficients. 1, there's 0x squareds. There is a negative 48x and then minus 128. And so if this comes up to 0, then we know it is a solution. 1 times 4 is 4, that's 16. Yeah, 1, 4. 4 times 4 is 16, that's negative 32. That's negative 128. This does not come up to 0. Comes out to negative 256, so we'd answer no, it's not. It did not divide into it evenly. The other way you could do it is find the f of 4 and see if that gave you 0. But if we remember the remainder theorem, if you crank out the math on this, it'll also give you negative 256. Number 6, we just have to sketch the graph of this. And they have a key note here, though. They tell you what these zeros are. And that's very important because remember, zeros for a polynomial are also the x-intercepts. So if we have to just make a little sketch here real quick, it looks something like this. X-intercepts at 4, and then at 8, and then at -4. So we'll put points right there because we know it's going to cross right there. This is a cubic equation, so it's going to go like this, one end up, one end down. We just have to decide, does it go up on the right-hand side, or is it going to look more like this, or it goes up on the left-hand side? The way we determine that is it's got a lead coefficient in front of the x cubed that is positive, and positive lead coefficients cause it to go to positive infinity. And so we know it's going to head off this way, and we know it's going to cross, so then it's going to have to turn around, it's going to have to come over here, it's going to have to cross, and then head back down. And we're done basically with our graph. Now there is another key point we usually like to locate, and that's this point right here, the y-intercept. So let's find the y-intercept real quick. It's the easiest thing in the world, because remember, if you're the y-intercept, your x value is 0. So we just plug a 0 in for all of these x's, and it causes all those things to turn to zeros, and your y-intercept is just 128. So that would be another key point we'd want to look for. Let's find the inverse of this power function. Now, in class, when we got to the inverse part, I did a little diatribe on it to try and explain why and how, but we'll just go through the basics of how you do it. Okay, so the steps are: first, change f of x to y. Okay, I'm going to erase a little bit of our work here so that we can have a little room there. So step 1, you're going to change x to y, and so this function that we're dealing with would become y equals x plus 4 cubed. Okay, so we haven't changed it at all, just changed the f of x to a y. Step 2 now, flip-flop or switch or exchange. I'm going to use exchange x and y. I'm going to put my y here in pink and my x here in red so you can see what happens in step 2. In step 2, the y becomes an x and the x becomes a y. Yeah, just flip-flop them. And then in step 3, you have to solve for y. So now that we have our x and y exchange, we want to try and get this y alone. So just look at what's being done to it. It's got y plus 4, and it's cubed. So to get to this y, what we're going to have to do is cube root it to undo the cubing. So I'm just going to cube root that, put a little 3 there, and cube root that. And I'm just going to get the cube root of x on the left side equals, on the right hand side there's no longer that cube because I've cube rooted it. And see, now my y is outside of this radical, or this cube that it was in, and I can just subtract the 4 and y's alone. And that's it. Those 3 little steps there. So I subtract this 4, and you see I get y equals, and then the way you can write this, I don't know, maybe like this would be a good way to write it. Probably the most standard way, because once you reverse it and put the y on the left hand side, that'll look better to us then. And so this is some sort of cube root function. Okay, it looks like it's going to be shifted down from 4 if we knew what the cube root function looks like. And so this is f inverse, okay, the inverse of this function. And we have a special notation for inverses. If this is the inverse of function f, we write f inverse, and then we say our equation. So that would be the full statement of what the inverse function is. Alright, now we're going to simplify a few radical expressions. These should be most fresh in our minds because that's what we've just been working on. So let's see here, we got a 54, remember this is a square root right here, so we're looking for two of a kinds. So 54, let's see here, 9 times 6, and 9's a perfect square, I like that one. And then I've got that x cubed. But remember to think of the x cubed in terms of even amounts, so I want to think of x cubed as an x squared times x. Because now I've got some things I can square root. I can square root the 9, and I can square root x squared. Square root of 9 is 3, square root of x squared is x, and then left inside the radical is that 6 and that extra x. And so there we go. Problem 9. Simplify. Looks like we got to add and subtract here. We got a negative out front. This is a root 2, so this is like 5 negative root 2's all added together. There's a 4, so root 3 added to itself 4 times. Remember, these coefficients just count how many root 3's you have. And this is 5 root 8's. Now, none of these can be simplified except this last one. And if you remember how we simplify, we use the multiplication rule for radicals, which says if I write it as a 4 times 2, I can separate them. And so now this is just 5 times 2, so 10 root 2. Now that's all the steps to what we're doing there, but hopefully we now know that the square root of 8 is just 2 root 2, and so it's 10 root 2 right there, 2 times 5. Okay, so we've got negative 5 root 2's and 10 root 2's. That's a total of positive 5 root 2's, and then we got the 4 root 3's, and they can't be combined, so we just leave them like that. Problem number 10. I'm going to just distribute my root 2. It's negative 3 root 14, inside times inside. Distribute it there, and I get 5 root 2, and I'm done. I can't add those. Got a radical equation to solve here. Step number 1, get the radical alone, please. You need to do that. Now we can square both sides, and the radical is gone, and we can see that x is 8 just by subtracting 1. You can check it real quick. 8 plus 1 is 9. The square root of 9 is 3. Negative 3 times 3 is negative 9. Number 12 here. All we got to do, radical is already by itself. We just have to square both sides. It gets rid of the radical, equals 16. And now, to get rid of that 5 down there, we'll multiply both sides times 5. Looks like that'd work if we put in an 80 right there. 80 divided by 5 is 16, and the square root of 16 is indeed 4. Just a couple more here. Here is number 13. This is to test to see if you realize you have to first factor. In this case, there's a GCF of 5x we can take out. That you have to factor before you can cancel anything. So now that we have factorizations, you got a 5 up here, an x and an x minus 3. Down here you have a 10 and an x. So think of that 10 so you can really see what's going on here. I'm going to write it like this. You don't do this, but this is kind of the way our brain should think. See that denominator, that 10x, that's a 5 times 2 times x, so we can cancel out these common factors like the 5 and the x. And so we just end up with x minus 3 over 2. That's what it simplifies to. Now this is all assuming, when you have fractions like this, you always need to check that denominator. Assuming that x does not equal 0, because if x is 0, 10 times 0 is 0, and you can't divide by 0. So this simplifying works as long as x is not 0. See here, problem 14. We got multiplication, that's good. So we got a 5 times an x minus 1 in our numerator. And our denominator, that's a difference of squares. X minus 1. Plus 1, and it's times 10. So again, I want to see everything written as multiplications, Even that 10 you could see as a 2 times 5 if you wanted to, so that I can see the things that cancel out. And in this case, x minus 1 does. And that again, as long as x does not equal 1. Because right down there, remember, you can't divide by 0, and 1 minus 1 is 0. So we can cancel those out as long as x doesn't equal 1. And 5 over 10 simplifies to a 2. So everything canceled out of the numerator, so that's just a 1. And we got an x plus 1 down there. We also have a times 2, so we'll put the 2 right in front. And number 15. Now 15, you would not know how to do this unless you watch this video or pay attention to class or look it up. These are pretty easy. Write this expression in exponent form. So what you need to understand, in brief summary, is that if I have something in what's called exponent form or exponential form, notice my x is up here in the exponent, I can change that into what is called logarithmic form by writing x equals log base b of y. And so if you can track this conversion, even if you don't know what this means yet, doesn't matter. Okay, what matters is if you can convert from this form, logarithmic form, into this form, and vice versa. Okay, so let's go ahead and I'm going to take this, I'm going to put it right by this equation we have here so we can compare parts. Now, we have to think about what we're moving in terms of location. X minus 5. Alright, so if you take a look, this right here, the x, it's the exponent, okay, from the logarithm. In fact, that's what logarithms essentially tell us. They help us or tell us what an exponent is in an equation like this, or help us solve for it. So the whatever it's equal to, that goes in the exponent spot. So we're just going to go like this. We'll say y is in our exponent. Notice the b here, that's the base. I'm going to write my base first. See, oh crud, this one did not have a base. I should have told you about the base. So this says 10 to the y power equals x minus 5. And so I've written this b, instead of b, I wrote a 10 there. The 10, if they don't show you a base, that is always going to be a 10. It's called the common logarithm, and they just don't show it. Just like in square roots, we don't show the little 2. In logarithms that are base 10, we don't usually write the 10. But you can see the logarithm tells you the exponent. So this reads in logarithmic form, x, this exponent, is equal to the log base b of y. We'll go over a few of these things in class. Hopefully you can understand them just a little bit better than I just explained it. And I think that is it for this page.